Level 3 highway driving assist systems operate in one of the most demanding physical environments, high-speed, multi-lane traffic where variables shift in fractions of a second. In these environments, we encounter a structural paradox in system safety. An autonomous vehicle can execute its programmed code flawlessly without a single hardware malfunction and still cause a fatal collision. To understand why, we have to look at how we've traditionally defined safety. Functional safety, governed by the ISO26262 standard, is designed to guarantee honest execution. It strictly prevents random hardware faults and software logic errors. But perfect hardware isn't enough. We also need competent execution, which is managed by ISO21448, or SOTIF. If the CPU is working perfectly, but a camera is blinded by severe pixel saturation from sunlight, the system can still miss a critical object detection. SOTIF requires the system to recognize this pixel saturation, not as a broken component, but as a functional insufficiency. The hardware is fine, but the environment has exceeded the system's operational design domain constraints. Relying solely on honest execution leaves the vehicle blind to environmental realities. True safety requires fusing internal hardware diagnostics and external situational awareness into a single unified architecture. Historically, automotive engineering has relied on a specific response to detected faults, the immediate fail-safe transition. If something breaks, the safest action is to shut the system down completely and hand control back to the driver. That approach becomes highly dangerous at 100 kilometers per hour. A sudden loss of steering or braking practically guarantees secondary collisions. Because of this, Level 3 and above systems require a fail operational architecture. The vehicle must maintain enough functional capacity to maneuver itself safely out of active traffic, even after a critical failure. We have to shift from defaulting to a static safe state to executing a minimal risk condition, or MRC. Instead of halting in the current lane, the system calculates a trajectory to carefully cross lanes and reach an isolated shoulder. Reaching that minimal risk condition requires the system to independently plan and execute a dynamic driving task fallback maneuver without waiting for human intervention. Achieving this level of fail operational capability is impossible when your safety systems are siloed. It requires building an integrated dependability cage that monitors both the physical vehicle and the world around it. The foundation of this dependability cage is the physical and electrical layer. It monitors internal hardware health, mapping connections between the ECU, power supply, and communication buses. Here, ISO26262 mechanisms protect data integrity, utilizing error correction codes and real-time checks to validate signal integrity. The timing requirements at this layer are incredibly strict. If an electrical short or a physical disconnection occurs that qualifies as an ASIL-D critical fault, the architecture must detect it within 100 milliseconds. To see how this translates to a technical safety requirement, consider a forward-facing radar used for object detection. The requirement dictates end-to-end protection mechanisms must guarantee the absolute integrity of the radar's communication data, from leaving the sensor to reaching the processor. This rigorous self-diagnosis establishes the system's baseline availability, confirming the hardware is ready to function. However, while this physical layer guarantees the hardware can act, it has no capacity to determine if those actions are actually appropriate for the external environment. That external context is processed in the second layer, situational awareness and performance monitoring. This level evaluates SOTIF requirements, mapping environmental data onto the hardware. It continuously calculates a confidence score for sensor quality. An active anomaly monitor scores inputs based on clarity and consistency. The primary goal here is to identify triggering conditions, specific moments where external factors exceed the system's predefined performance limits. Continuing our radar example, if real-time visibility analysis detects heavy snow, the system must recognize that its physical braking capability is compromised. It can no longer prevent collisions at this speed, even if the electrical components are flawless. The required architectural response is proactive. The system must dynamically downgrade the target speed to match the environmental limits, regardless of what the functional radar detects ahead. Consider lane keeping on curved highways. A camera's perception dictates one path, while HD map data dictates another, due to construction. The function monitor tracks this divergence. Upon a threshold alert, it lowers HD map confidence and shifts driving authority to the vision model. This specific logic check prevents catastrophic steering deviations when a GPS signal drops out in a tunnel or a mapped route no longer matches reality. This cognitive layer acts as a constant reality check, ensuring the system only trusts its inputs when environmental conditions allow, preventing the blind execution of flawed data. The apex of the dependability cage is where internal health and external reality converge, the hybrid logic and decision layer. Information flows upward from both the physical and cognitive layers, meeting inside a central arbitration logic matrix. This layer operates as a safety shell. It's an independent channel that constantly validates the nominal AI's path planning against the strict laws of physics, ensuring every intended movement is actually possible. The core function here is prioritization. The matrix must process conflicting data and dictate the correct system response based on a strict hierarchy of risk. Priority 1 focuses on physical control. If an ASIL-D critical hardware fault occurs, like a total steering unit failure, the matrix prioritizes an immediate transition to a safe state to prevent uncontrollable physical behavior. Priority 2 shifts to environmental hazards. If the hardware is healthy, but SOTIF limits are severely breached, meaning the vehicle has exited its operational domain, the system rejects a sudden shutdown, initiating a fallback maneuver to reach a minimal risk condition. Priority 3 handles compound issues. If non-critical physical faults combine with poor environmental conditions, the system enters a degraded mode, maintaining availability but strictly limiting the vehicle's speed. The arbitration logic acts as the ultimate judge. It weighs the integrated safety scores from both standard protocols to dictate the vehicle's exact maneuver state, and it must do all of this within 500 milliseconds. Once a decision is made, we enter the final execution phase. The arbitration logic commands the physical steering and braking actuators to achieve that minimal risk condition. ISO26262 requires these actuators to be fail operational. Even after a single point fault, a dual-coil power steering motor must maintain at least 50% of its torque output for a minimum of 30 seconds. ISO21448 builds directly on top of that physical requirement. The system must use that remaining 50% steering capability to calculate and execute a smooth trajectory to the nearest safe zone. During that brief 500 millisecond trajectory generation window, the system evaluates the density and speeds of surrounding traffic to avoid secondary collisions while pulling over. Achieving a minimal risk condition relies entirely on this fusion. Functional safety provides the physical resilience to stop the car, and SOTIF provides the environmental intelligence of exactly where to stop it safely. Validating an architecture with this level of interdependence renders legacy, siloed testing methodologies obsolete. Traditionally, functional safety relied on fault injection testing to isolate and break hardware. SOTIF, conversely, relied on scenario-based simulations to test algorithmic edge cases. The modern solution is integrated co-simulation. Engineers inject environmental noise, like fog, while simultaneously forcing memory bit flips into the hardware. This forces arbitration logic to process compounding threats in real time, verifying the system rejects nominal operations and correctly commands a degraded mode with adjusted speeds. This simulated testing must be paired with continuous real-world data collection, feeding an iterative safety lifecycle that constantly converts unknown edge cases into known risks. Without subjecting the arbitration logic to these compounded stress tests, the dependability cage remains purely theoretical, and the system cannot be deployed on public roads. They must break down traditional organizational silos. Functional safety engineers and SOTIF specialists have to merge their workflows and share a single unified safety goal from day one of the project. They must also implement the safety shell concept to constrain the unpredictable black box nature of AI models, surrounding them with strict physics-based boundaries. Level 3 and above autonomy requires the vehicle to achieve honest execution and competent execution simultaneously. Neither standard can accomplish this alone. Only through a meticulously designed, dual-layered dependability cage can we build systems with the resilience necessary to push residual risk below the threshold of social acceptance, making reliable autonomous driving a reality.